For part 2 on chapter 11, we will look at sections 2 to 4. In section 2, we'll focus on RAM, random access memory. And by the end of this section of the lecture, you should be able to fulfill the following learning objectives as listed in the slide. So there are two main categories of RAM, that is SRAM and DRAM. SRAM being static RAM, DRAM being dynamic RAM. The difference is that SRAM uses latches as the memory elements, which require power in order for them to keep record of what's in memory. So as long as there's DC power, the SRAM will be able to store data. But as soon as power goes off, the data is lost. So it's a volatile type of memory because of that. Whereas DRAM uses capacitors, which require refreshing. So as long as there is power from time to time, even though there is power from time to time, the DRAM will require to be refreshed. That is, the data will require to be rewritten onto the DRAM so that it's not lost. So that's one advantage that SRAM has over DRAM. And SRAM is much faster than DRAM, but SRAM is more expensive than DRAM. DRAM is cheaper and it's more compact. Looking at those individual types of RAM, you will see that SRAM has two types, two subtypes, which is asynchronous SRAM as well as synchronous SRAM with burst feature, which is SB SRAM. The asynchronous and synchronous simply refers to the system clock. For asynchronous RAM, the processor's clock is not tied to the RAM, whereas in synchronous RAM, the processor clock or the system clock also controls the RAM as itself. There are also four types of DRAM that are available. The first type is the first page mode DRAM. The second type is the external data DRAM, the burst RAM, and then the synchronous DRAM. This figure shows the basic memory cell of an SDRAM, and as initially stated, this is a basic latch, and it has three pins: the select pin, data input pin. Two of these are inputs, and then there's an output pin, which is a data out. So the data is written first by enabling the select line. So the select line is held high, and then whatever data that's on the data input will go through into the latch, and the data is spread out through data out by simply reading out the bit that's on data out. This shows an example of an SD memory array. We can see that in this case the array has multiple rows. This would be n rows, and each of these cells, it's basically the latch which has the select lines. So the select lines are all connected with the row select, and the lines that go down to the data IO buffers, these are the input output lines. So this would be the input line, this would be the output line, this would be the input and output line. Because with an SDRAM you can read and then write to it. As a RAM block, the array can have the following inputs and outputs. So it will have address lines, or typically what's called an address bus. So generally speaking, a bus here simply means an electrically conductive path So whatever connects to this address bus, all of these 15 lines here will be called an address bus. And then there is also this output. So it has it stores each time 8 bits. So this would be the data bus. This would be the data bus. And then the triangle here, the triangles here which are upside down, they indicate that the output is the input output here, or the data bus is almost tri-state buffer. So tri-state buffer allow this bus to act as both input as well as output. And then you have these other 3 lines, which is the chip select, the write enable, as well as the output enable. All of these 3 make up what's called the control bus. So the control bus will have the chip select, write enable, as well as the output enable. So the figure below shows a read operation for an SRAM, and a read cycle. The length of the read cycle is called TRC. In this case, this is the length over which a valid address must be placed on the address bus. Now, this TRC depends on a number of durations. For example, it depends on TGQ. So once the bus has been put on the address, what then happens is that the chip select will be held low to enable the chip, and then the output enable will also be held low. And once that happens, after some time, the data will begin to appear, valid data will begin to appear on the data output, that is the output on the data bus. Now, the time duration called output enable access time, TGQ, is the time it takes for the enable to go low, is the time it takes between the output enable going low and a valid data appearing on the data bus. There's also another time which is called output chip select, TEQ. TEQ is the time that the chip select goes low. It's the time duration between when the chip select goes low and when a valid output data on the bus appears. And TAQ is another time that can be used to characterize the read operation of a valid SRAM memory module. It's the time between getting a valid address and then getting also is the time between placing a valid address on the address bus and getting a valid data on the data bus. So clearly the read operation must always last longer than at least TAQ, because then if TRC is shorter than that, it means the memory or the read operation will end before valid data is seen on the data bus. So nothing will be read from that memory chip. Here we see an example of a write operation, and the write operation cycle time is TWC long. This write operation shows the operation of writing a single block of data or piece of data into the memory. So TWC, it simply specifies the length of time over which a valid address must be held so that data can be read or can be written into the RAM. And it depends on other durations as shown. So typically what happens is that when data is written into the memory, first of all the chip select will go low, and then the write enable will go low so that so that the memory can accept incoming data. And then after some time, the valid data will be shown or displayed on the data bus. And then there will be a time that needs to pass after valid data has appeared, whereby the valid data, there will be a duration of time whereby valid data has to be on the data bus, and that time is called THD. So the durations that make up TWC would be, the first one here is TSA. TSA simply means address setup time, and the address setup time is the duration of time, the minimum duration that happens between having a valid address on the address bus and the right enable going low. That would be address setup time. And then after that has happened, there is a time which is called write enable. There is a TWD. The TWD is the shortest period of time that the write enable must be down so that valid data is written into the memory. That is TW. And then we have finally THD, which is the data hold time. This is the necessary amount of time over which that data that we need to write must be held on the data bus so that the write operation is valid. Having discussed generally the operation of asynchronous RAM, let's now look at the difference or the operation of synchronous bus RAM. So the defining characteristic of synchronous RAM is that it uses the system clock, that is, it's synchronized with the processor, and the SRAM has clocked registers. So it has a number of registers which are clocked, and the active clock pulse edge is able to latch in input data, chip enable data, read data and write data and address data into those clocked registers. So there can be two types. There are two types generally of SB SRAM, which is the flow through type and the pipeline type. The difference here being that for the flow through type, the data output register is not available in the flow through type, whereas in the pipeline type, the data output register is also there. So for the flow through type, the data is available asynchronously, so it just flows out asynchronously, whereas in the pipeline type, even the data outflow is synchronous. This is an example of a structure of a synchronous bus SRAM, and you can see here, as previously explained, that there is a clocked address register, so it goes with the clock, and then there's a clocked write enable register here. Chip select register is also clocked, and then you also control the output enable, and you can see also that the data register, the input data register here is clocked. And the difference here is that for a pipeline type, there will also be data output register which is clocked. However, if it's flow through, this will not be there. So the output will simply go straight to the output buffer. What you will also see as well here is that the address register, as much as it latches the whole of the address into address register, the address register connects to the address decoder to pinpoint which part of the memory needs to be accessed. However, there is here also some parts of the address which are being controlled by the burst logic here. So this burst logic circuit is the one that allows this register to operate in burst mode. So the burst feature simply allows the It allows multiple memory regions which are adjacent to be sequentially accessed, even though only a single address has been specified. So it allows memory to be read or written for up to 4 sequential locations using just a single address. So when the memory is addressed with a single address, the burst feature allows that address to read the next 4, in fact the adjacent 4 addresses sequentially, even though only one input address has been placed onto the address bus. And the structure of the burst logic is that it contains the clock and the burst control, and the main feature of the logic is a binary counter, and the binary counter whose outputs are linked to the 2 lowest bit or the 2 least significant inputs of the address bus. Now what simply happens is that the counter, in fact, when a specific address has been specified, the counter here will ensure that as it changes its sequence, in this case we have a 2-bit counter from 0 to 1 to 2 to 3, that is 0 0 0 1 1 0 1 1. As it changes that sequence, this will change the addresses at the input of the address decoder, allowing the memory to access all four adjacent memory locations, even though only one address has been specified. Another type of memory which is of interest, it's called cache memory. Cache memory is one common application of SRAM, and cache memory is normally a relatively small high-speed memory unit which stores the most recently used instructions or data, and it's just meant to avoid the frequent use of main memory, which is much slower. The cache memory is analogous to the case of a refrigerator to a supermarket. If you imagine a cache memory as a refrigerator and a supermarket as main memory, so imagine if you require a certain item, say you require some refreshment in the form of a juice, you would first then check if there is that juice in the fridge, in which case if you find it, it means you have saved time to go to a further away place, which is a supermarket. But if you don't find it, then you have to go to the supermarket. So this is the same with the way the processor accesses main memory as well as cache. So it will store some of the data that it might frequently need to use. It will guess what data it might need to frequently use and then store it in cache memory. If as and when it needs to retrieve that piece of data, it goes first to the cache to check if that data is there. If the data is there, it saves time and it's able to execute quickly. But if that data is not there, it has to go back to the main memory to try and access that data, which is much slower. And you will notice that first of all, there is a trade-off between the cache and main memory, in the sense that the fridge, you can't buy the biggest possible fridge and store everything within the fridge, because there's a big cost towards buying the fridge, whereas the supermarket is almost free in terms of storage because you don't have to pay for things stored in the supermarket. So cache memory is quite expensive as compared to main memory in that sense. It's expensive even though it's faster, so you need it to speed up your processing time. However, you cannot get enough because it's costly. Otherwise, the computer system becomes very costly. So there are different levels to cache memory. Typically, there will just be 2, level 1 and level 2. Sometimes they could be as many as 4, level 1, 2, 3, up to 4. So the level 1 of cache is normally called primary cache, and this is normally incorporated in the same chip as the microprocessor. This is the most expensive part, so it's internal to the microprocessor. The second it's called the secondary cache, which is an external chip, and this can be where the SRAM can be used. And the way the setup will work is that there will be a cache controller which is synchronized to the processor using the system clock, and the cache controller will be able to access information from the cache as well as the main memory, whereby it can take some information from the memory and store it in the cache. In this case, then, whenever the processor wants to access information from the cache, it does that via the cache controller, and the cache controller can be able to state if that information is available within the cache. The DRAM, as previously stated, stores data within a capacitor, and therefore this provides for a simple and compact structure as opposed to the SRAM, which is based on a large as its memory cell. This makes the DRAM much cheaper, and also DRAMs the memory can be packed into smaller structures. However, the disadvantage of DRAM is that it needs periodic refreshing, as the data tends to leak out of memory. So even if there is power, after some time, from time to time, the data will need to be refreshed so that it's not lost. So the DRAM, typically, a data cell for a DRAM would be made up of two things, that is a MOSFET transistor as well as a capacitor. MOSFET meaning metal oxide semiconductor field effect transistor. This series of pictures A, B, C, D shows the operations of a typical DRAM. So the DRAM would have, in this case here, we are looking at storing a 1 inside the DRAM cell. So what will happen is that the row select will go high to select that particular cell, and the data in would be high to show that we are storing a 1. So this 1 will pass on into the bit line, and because the row select is high, the transistor will be on, and when the high voltage is experienced here at the bit line, this will begin to charge the capacitor to store the charge, so that when the capacitor is fully charged, then it will contain the binary bit 1. On the contrary, when 0 is being stored, what tends to happen is that is when you are writing a 0 into a DRAM cell. What will happen is that the MOSFET gate will be switched on, and however, the data at the input will be low, which means this will be 0. And so what will happen is that whatever charge in the capacitor, it will begin to flow out up until there's no charge at all. So this will store a 0 inside the capacitor. In the case of a reading operation, we can look at examples C and D. If at C, we will see that if a 1 is stored, for instance, in example C, the row select here will be high, and once that is high, what will happen is that then whatever charge is inside the capacitor will conduct out into the bit line, and this will be read at the data output as a 1. So remember, from time to time, like we said, the capacitor will leak as and when the memory is operating, and because of that, the data will be lost. So to avoid this, the DRAM has a mechanism whereby it keeps on refreshing at a certain period of time, after a certain period of time. So the refreshing operation works as follows. In this case here, the refresh line is used to update the one that has been stored in this memory cell. What happens is, from time to time, the row select will be high, and then a 1 will be on on the refresh buffer, and that one will begin to recharge the capacitor, because now the MOSFET key will be open because of this row that's high, and this will restore all of the charge that has been stored to make sure that the one remains in the memory cell. This gives an example of a DRAM memory array. You will see in this case, what's interesting is that the memory array has a logic for refreshing. So this is a refresh control and timing and refresh counter. And the purpose of this logic is to ensure that from time to time, the contents of the memory array are updated or refreshed. You will see that the address register is connected to both the row and the column decoder, and the CAS and the RAS lines, control lines, are used to multiplex between the row and the column decoder. For the basic operation of a DRAM, so what happens is that the single address, the same address bar, is used to address both the columns and the rows. And so because both the columns and the rows address is interchanged, you have the row access select and the column access select being used to read either the row addresses or the column addresses. So the row access select will go low to read in the row address. That is, it will latch this row address select, it will latch the input of the address into the register, and then afterwards the column access will latch the input of the column address into the register, and both of these addresses will then be transferred to the decoders, respectively the row and the column decoders, to later access the memory location. Another type of access is called fast page mode access instead of the basic operation. And to understand fast page mode access, I need to define first what we mean by a page. A page, in terms of the DRAM, it simply means memory that's available on a single row. That's what a page is. So if you have a single row of memory, all of those columns in that memory, it's called a page. So in fast page access mode, what happens is that the DRAM is configured to read many or all of the columns in quick succession of a single row that has been selected, instead of simply latching in first the row address and then a particular column address. What the memory will simply do is it will take only the row address and then in quick succession read all of the column addresses. Recall we have initially emphasized that a DRAM requires refreshing in order for it to maintain the data in storage, even though it's powered. So the refresh needs to happen each and every several milliseconds. The read operation automatically refreshes all of the data addresses in the selected row, which means if we were sure that each and every row was being read, then we wouldn't need to refresh the memory. However, since this cannot be guaranteed, the memory array has a special refresh cycles. Then this can be implemented either as burst refresh or distributed refresh. In burst refresh, all the rows in memory are refreshed one after the other periodically. Whereas in distributed research, each row is refreshed at a certain interval, and this interval is spread between the normal read-write cycles, because remember we said the normal read-write cycles also act as act to refresh the memory automatically. There are also several types of RAM, as we have alluded to initially. And the first type of RAM is the fast page mode DRAM. And this DRAM, as the name suggests, is based on the probability that the processor would need adjacent memory locations. So if one memory location is read, those close to it are going to be needed. So what happens is the DRAM simply reads, as always, in fast page mode, in the sense that when a row is selected, it reads all the adjacent columns data out, and this happens to save time as opposed to purely random access if and when the processor requires all of this adjusted data. However, it will then tend to waste time if the processor does not need to access all of the adjacent data. Another then improvement over the fast page memory DRAM is called the extended data output, the extended data out DRAM, also called the hyperpage DRAM. This is an improved FPM DRAM which speeds up page access. Another enhancement on top of the extended data out is called the burst extended data out, which is the EDO DRAM, which has now been put or given the burst capability as initially explained. And then later came the SRAM, which is the synchronous RAM. Now, the idea of a synchronous RAM is that like the SRAM, the DRAM is built so that it's synchronized with the system clock so that the processor can access it much faster. And like the synchronized SRAM, all of the inputs, address and control data are latched into a register so that the memory is synchronized with the processor. An improvement on top of the SRAM, SDRAM is the DDR RAM. The DDR SDRAM is activated on both edges of the clock. In this way, the DDRAM is able to perform two operations, that is two read operations or two write operations per clock cycle instead of just one. That's done by the SRAM. At this point, we'll look at read-only memory or ROM. We'll list the types of ROM and should be able to describe the basic ROM, mask ROM storage cell, explain how data is read in ROM from ROM, and discuss the internal organization of a typical ROM. Read-only memory ROM has different types. There is the basic ROM, which is called the mask ROM. There could also be programmable ROM, erasable programmable ROM, EEPROM, or the ultraviolet erasable programmable ROM, or theoretically erasable programmable ROM, E2PROM. ROM is permanently programmed during the manufacture process, and it can only then be read afterwards. The way it's programmed is normally the zeros and ones are programmed normally by the lack of or the existence of a connection wire with the transistor. For example, if we look at an example of a ROM storage cell, that is the transistor here, which is storing a 1. It's storing a 1 by virtue of having a connection between the row itself. So what happens is that when a row is selected, that is a high is placed on the row, the data is read through the column, and this data will be 1 because the 1 that has been placed on the row will be transmitted through the transistor to activate the transistor so that this line is high, and this will show that a 1 is stored. However, if a 0 is stored, what happens is there is no connection between the row and the transistor gate. So what will happen is that when a row is selected, because there is no connection here, the voltage here will remain at 0 and a 0 will be read on the column. An example of a ROM can be, for instance, a binary to Cray decoder. This is an example of a 16 by 4 ROM. Recall that when we have a binary to Cray decoder, we have a code where, for instance, 000 quadruple 0 corresponds to quadruple 0, 1 corresponds to the normal one that we know. However, binary 2 corresponds to Cray code, which looks like binary 3, because in Cray code only 1 bit changes between the sequences. So if you look at a case whereby the binary input to the ROM is 2, that is, you have 0, 1, 0, 0. The output of this would select here, it will be 2. So this is the row that will be selected. And because this row will be selected, the output will simply be 0, 0, 1, 1. And this output will be the same as this row. And in so doing, here we will read the number 0011. So this could be an example application of a typical ROM. The internal structure of ROMs is usually more complex than it looks from the outside. Looking at an example of a 256 by 4 ROM, whereby there are 8 bits, there's 8 bits of address addressing 256 locations, each with 4 bits, which means the data output of this particular ROM is going to be expected to have 4 bits, and the control bus is simply 2 chip select lines. If we look at the internal structure of how this is composed, we will see that in fact the internal structure has to be composed of a much bigger memory, which is 32 by 32 array of memory. And what happens is that the first 5 bits of the 8 will address the rows, the 32 rows of the memory. And the final 3 bits will tend to select the 4 columns that are going to show up at the output. So on top of having a 32 by 32 array memory, there is a combination of 4 decoders which have to be selected. These are 4 1 to 8 line decoders, as well as a row select. And this is much more complex than a typical structure of any other type of memory for a given simple 256 by 4 memory size. One of the performance measures of ROM, it's called access time, and access time is measured as the time difference between the application of a valid address on the address bar and the appearance of a valid data output on the data bus. And this is the gap that we're talking about. So the shorter the access time, the higher performance of the ROM. The last section of this part, section 4, talks about programmable ROMs. So at the end of this section, you should be able to distinguish between mask ROM and programmable ROM. Describe the basic programmable memory cell and be able to discuss EPROMs, including UV EPROMs and EE EPROMs, analyze an EPROM programming cycle as well. Programmable ROMs use the fusing process to store bits, and memory of a programmable ROM will have fuse links as well as the MOSFET transistors linked to them. So the memory link is bent open or left intact to either store 0 or 1. Fusing is irreversible, and once programmed, it can't be changed. Generally speaking, the programmable ROM can be changed. The difference between mask ROM and the programmable ROM is that the programmable ROM is field programmable, and you program it whilst in the field. You buy a blank chip and then program it afterwards, whereas the masked ROM is programmed from the factory. There are 3 types of fusing technologies that can be used in programmable ROMs. It can either be metal links, silicon links, or a PN junction. Metal links are made up of material such as nichrome, which is an alloy of nickel and chrome, and these metal links are blown open or left intact during the programming phase. In order for a particular link to be blown open or left intact to be programmed, it has to first be selected in the address. An alternative to this is a silicon link, which is made up of narrow notched strips of silicon, polycrystalline silicon. So the fuses are made of polycrystalline silicon as opposed to the metal in the metal links. And programming involves passing current through the silicon link, which results in a high temperature, and this high temperature oxidizes the silicon. This silicon then it forms an insulation which results in an open link. Or skipping that part, part of or that memory cell if the link needs to remain intact. A PN junction link, in this case, the link is made up of 2 back-to-back PN junctions, and the programming involves shorting one of the junctions. One of the junctions shorted and the other is left intact so that it can be used to read out the data. So there is a type of a programmable ROM called an erasable programmable ROM. As the name suggests, an erasable programmable ROM can be erased, can be reprogrammed if first all of the previous information has been erased. So an EPROM can be reprogrammed. It uses an N-MOSFET array of transistors with isolated gate structures. The bits are presented in a form of an absence or a presence of a gate charge that has been stored in one of these MOSFETs. An example of an erasable programmable ROM, EPROM, erasable programmable ROM, is shown in this figure. To program the device, you will notice that the device has an input VPP as well as an input output enable. So to program the device, a high is placed on the input VPP as well as the input OE, and in this way the electronic programmable ROM will be able to be programmed with new data. There are 2 common types of EPROMs, the first being the electrically erasable PROM, The second being ultraviolet eraser EEPROM, the UV EEPROM. So the distinguishing characteristics or the important issues here is that the EEPROM can be erased quickly because it's electrically erased, and the EEPROM can either store. So there are two types. It can be one which stores, which works or which uses floating gate MOSFETs, or it can be the one that uses a metal nitride oxide silicon type of a transistor. For the UV EEPROM, erasure is done by exposing the memory array chip to high intensity ultraviolet radiation using the opening that will come with with the array itself. So there will be a particular slot or opening on the array whereby if one exposes that particular portion of the memory to ultraviolet ray, then that erases the memory of the EEPROM. At this point, we have now looked at RAM. We have also looked at ROM, and we have also looked at programmable ROMs. Please consult the end of the chapter sections for test problems that you may attempt in order to cement the concept.